All right. Hello, everyone. My name is Laura Molares, and I am a PhD student in polar geomicrobiology and working with the ICCI this week at the Cryosphere Pavilion. Today's theme will be all about feasible pathways to 1.5 degrees and emission reductions. Our first session of today is Scientific Revisions, Policy Decisions, Climate Effect of Black Carbon in the Arctic, organized by Arctic Monitoring and Assessment Program with speakers from Cicero, NILU, Finnish Met, University of Leeds and the Arctic Athabascan Council. Thank you and welcome.
Thank you, and good morning, everyone. So welcome to this first session at the Cryosphere Pavilion. My name is Maria Kvalvåg, and I am the Deputy Secretary of the Arctic Monitoring and Assessment Program, and I will moderate this session today. Today's topic is short-lived climate forcers in the Arctic, and we will hear about emissions of black carbon and how it contributes to a changing cryosphere. And we will also particularly focus on wildfires and emissions on wildfires and how it impacts the Arctic and the people that lives there. I would like to thank the organizers from ICCI, Iceland and Chile for hosting the Cryosphere Pavilion, which is an important platform for AMAP and others who are interested in the cryosphere and the Arctic. This is important for us to reach out with our findings and our reports and the urgent message about the cryosphere. So today we will have a variety of discussions and also pre-recorded videos since the internet is not working here today. And there will also be room for questions from you in the room. So the first presentation and speaker for today is Marianne Tronstad Lund. She's a research director at Cicero in Oslo, Norway, and a climate scientist in PhD in meteorology and a broad expertise in global climate modeling. She is also an expert to AMAP, and she has contributed to a new publication that is actually online today about the climate effects of black carbon emissions. So then we can have that video on. Thank you.
Hello everyone, greetings from Norway. My name is Marianne Tronstad Lund. I'm a research director at the Center for International Climate Research in Oslo. And I'm very happy for the possibility to speak to you today about black carbon as a climate forcer. Black carbon is a species of aerosols, tiny particles suspended in the atmosphere. It is a major component of fine particulate air pollution. Black carbon is the sooty material, or more technically, the light-absorbing fraction of elemental carbon, which is formed by the incomplete combustion of fossil fuels, biofuels, and biomass. Black carbon is emitted from essentially all sectors where there is combustion of these fuels. The importance of different sectors varies significantly between regions, but on a global scale, the most important is the use of energy for residential and commercial purposes, transportation, and industry. In contrast to most other aerosol species which scatter solar radiation back to space and contributes a cooling impact on climate, black carbon absorbs solar radiation. This is called the direct effect, or the aerosol radiation interaction. The particles also interact with clouds through several mechanisms, the so-called aerosol cloud interactions. Overall, black carbon is estimated to have a warming effect on climate. This is also why it has received significant attention as a way to limit climate warming, and at least in the short term. Regionally, there can be distinct features to black carbon's climate effect. The Arctic is one such region. For instance, the extreme seasonality in sunlight in the region affects the direct impact of black carbon. Clouds can also be uniquely different in the Arctic than in other regions. And there's a third effect at play in the Arctic. This is the effect of black carbon after it gets deposited on snow and ice. By darkening the surface and absorbing solar radiation at the surface, this gives rise to additional warming from particles. And this is one important reason behind the focus on black carbon as a driver of climate change. In the recent 2021 reports by the IPCC and the Arctic Monitoring Assessment Program, black carbon is assessed to have a warming contribution to climate change, both on the global mean scale and in the Arctic. The global mean effect on the Earth's energy balance was estimated in the IPCC report to be 0.1 watts per square meter, around the same order of magnitude as some of the other non-CO2 greenhouse gases such as N2O and CFCs. The contribution to temperature, which was assessed for the first time in the sixth IPCC cycle, is 0.06 degrees. For the Arctic, a best estimate effective radiative forcing of 0.96 was derived by the AMAP group. Note that the Arctic estimate also includes the important albedo effect, which constitutes a substantial fraction to the total net effects, as you can see from the light purple bar. It is important to mention that black carbon is co-emitted and coexists with other aerosol species, and this needs to be considered when assessing the net effect of emission mitigation measures. As you can see, these other aerosol species also have important contributions to temperature and radiative forcing, but of opposite sign. Despite significant progress, the magnitude of the black carbon warming remains highly uncertain. This is due to limited knowledge about black carbon sources, optical properties, and atmospheric processes such as transport and cloud interactions. The uncertainty bar even covers negative values. Moreover, estimates have varied strongly between recent assessments. Notably, there has been a lower estimate of the black carbon effect on the Earth's energy balance in recent reports as compared to previous studies. There are several reasons for this. One important reason is that there has been a shift in the metric that is used for estimating climate effects. Previous reports and assessments used radiative forcing. Later, there has been a switch to the use of effective radiative forcing. Effective radiative forcing is the change in the Earth's energy balance that is caused by a change in an atmospheric constituent. But in contrast to radiative forcing, it accounts for the so-called rapid adjustments that occur in the days and weeks after emission. For black carbon, it has been found that these rapid adjustments contribute to offsetting a significant portion of the positive or warming radiative forcing from aerosol radiation interactions, and thus lowering the estimate. There's also been improved understanding of the processes that link black carbon emissions to climate effects. For instance, how strongly the particles absorb sunlight, how they age, and how long they stay in the atmosphere. And finally, different sets of models have been used to estimate climate effects of both black carbon and other SLCFs and contribute to differences in estimates. While black carbon may have a smaller effect on global mean surface temperature than previously assessed, the best estimate net effect is still on the positive side, meaning a warming. Moreover, there is also important regional effects beyond temperature to be considered. Black carbon and other aerosols affect precipitation, extreme events, haze episodes, and the monsoon cycle, all of which contribute to posing key risks to society. Recent satellite constraints suggest also that a stronger effect of black carbon is possible and highlights the need for a more comprehensive reassessment of black carbon climate influence. Finally, black carbon is not acting or changing in isolation. Black carbon is co-emitted with and exists in the atmosphere alongside other aerosols. Understanding the full interactions and net effect of aerosols is therefore key. Finally, black carbon has severe detrimental effects on air quality and human health, and contributes to hundreds of thousands of premature deaths worldwide. Poor air quality is also a challenge in the Arctic region. Fairbanks, Alaska, for example, regularly experience pollution levels exceeding the air quality standards during winter and causing unhealthy air. Wood combustion is an important source of pollution, but coal and oil power plants, transportation, and other industries also contribute, as do meteorological conditions, which contribute to trapping air pollution close to the surface. There are therefore clear co-benefits from addressing black carbon. So to summarize with some key messages, black carbon, as well as other aerosols, play a key role in regional and global temperature, hydroclimates, and extreme events, although their magnitude remain uncertain. Policies to reduce emissions of black carbon are warranted, but action on black carbon and SLCFs should of course be viewed as a complement to reducing CO2 and other greenhouse gases. Clear co-benefits from addressing black carbon exists, in particular from air quality and human health perspectives. Research needs to be focused on better understanding the interactions between all short-lived climate forcers and to reassess black carbon's climate effect, taking into account recent scientific advancements. Finally, human-made emissions of aerosols are changing rapidly in many places and are expected to continue to do so in the future. Understanding the full implications on climate is therefore a key prerequisite for understanding near-term climate risk on society. And with that, I would like to thank you for your attention, and I wish you a fruitful and hopeful COP. Thank you.
Yes, so thanks to Marianne for that update on the climate effect of black carbon. We will move on to the next speaker, which is presented here in the room. That is Rolf Rødven, the Executive Secretary of Arctic Monitoring and Assessment Program. And he will speak to us about AMAP's work on science and knowledge to inform policy. So, Rolf, the floor is yours.
Thank you, Maria, and good morning, everybody. Okay, may I have the next slide, please? It's not, okay, maybe not. It's on. As you just heard Marianne talk about, it's recently been a discussion about the variability and bias in the estimates of black carbon when it comes to radiative forcing. And when it comes to science policy, that is an important thing, because whenever there's uncertainty, it also affects the actual will for policymakers. So for us, the rationale to bring this on the scene for policymakers is also to make them understand the reason for the uncertainty, and also to make them understand that even though there's uncertainty, there's a good reason to act on this when it comes to policy making. In particular for us, it's important because this is not working. There you go. Because black carbon has been one of those forces of what we call the Arctic amplification, or the reason why the Arctic is warming so much faster than the rest of the world. And we've been attributing that to part of that to black carbon. So for us, it's about understanding the Arctic amplification, but also because to mitigate black carbon do have a very short-term effect in terms of it takes a short term from the reduction to actually see an effect on the warming. A much shorter time span than we will see on CO2, for instance. So it is. It has its benefits also. Also on this. And also the Arctic is a perfect laboratory, perfect case study to exemplify it, because all signals are so clear. The Arctic is warming so much faster, so it's a very good case for showing this to international policymakers and bring this forward to the policy scene. However, when we do that, and we do so, all our reports feed into international regulations like IPCC, Stockholm Convention, Minamata Convention, and so on. However, when you do so, you have to be aware of how you do that. There's a difference between science to policy processes and outreach. It's not like a one-way process, but it's an interaction. So we've been going from like an understanding of science policy being from science to policymakers to where we are now, where there's an interaction between the policymakers and the scientists, but also between society. And in the Arctic case, the very important part of society is the indigenous peoples, because they are so much better than us to explain the impacts of the warming going on. Also, we have to, for us, we always are aware of the credibility. So we're not an advocacy body, we're a scientific or science policy body. So we are reliant on fulfilling both credibility, relevance, legitimacy, but also I would say in this case ethics, because it's a lot about ethics when you work with people of the North. AMAP's work, when it comes to science policy, works in a double loop. It is the interface between scientists and policymakers that define the policy relevant scientific questions. Those are combined by the knowledge we have that can fill policy gaps, the policy gaps that knowledge or that scientists do not know about, and those knowledge gaps we need to bring forward. And it works its way all through the process, and then back again to feed in the next cycle of science policy making and AMAP assessment processes. However, when we come to our reports, it's also very important for us to distinguish between what is science and what is policy recommendation, what is science and what is politics. So that is also why we always, when we do our reports, the scientific reports, which you can see on the left-hand side here, is a pure scientific report. The summary is also a pure scientific summary, only peer-reviewed, not negotiated, but with policy recommendations added on to make sure that we maintain the credibility as a scientific body in this process. And with that, I'll leave it for the next speaker. Thank you.
I will take advantage of Rolf being here in person since we have so many pre-recorded videos, so I will just ask you one question. It relates to AMAP being here at COP today, and that's of course an important science to policy platform for us to be. And if you could say something about what AMAP wants to achieve about being here at the COP.
It is, as I said, like there's no place on Earth where the Arctic is warm, where the global change is happening faster than in the Arctic. More than 3 times as fast as anywhere else. We have oceans acidifying 3 to 4 times as fast as any other ocean body. We have permafrost thaw, we have wildfires, which we'll hear about, which have quadrupled since 2010. So it is urgent for us, and it's urgent for us to bring the cryosphere and the Arctic on top of the table of the negotiators to understand that this is something that's happening now. It's not the future scenario, it's a scenario happening now.
Thank you. So thanks again to Rolf. The next on the program is another pre-recorded video. We will move on to talking more about wildfires and emissions from wildfires and the impact on climate. So now it will be 3 presentations following here. The first one will be from Sabine Eckhart. She's a senior scientist at NILU in Norway, and she will talk about transport of wildfire smoke to the Arctic. So the video can be on. Thank you.
Good afternoon. My name is Sabine Eckhart and I'm a senior scientist at NILU in Norway. My expertise is atmospheric transport modeling, and I'm especially interested in the Arctic. Therefore, I'm involved in the AMAP short-lived climate forces group. In the following talk, I will show you how wildfire emissions are transported into the Arctic. The emissions of wildfires are combustion products, which can be either gases or particles. In the following, I will focus on black carbon, as this is a substance which can be harmful to humans close to the emissions, but also have a climate impact due to its absorption properties. The emitted particles play a role in cloud formation. Black carbon warms the atmosphere by direct absorption and has the ability to decrease the albedo of snow. For the Arctic, mainly high-latitude wildfires are relevant. Satellite observation gives us a good information on the strength and location of wildfires. The map in the middle shows the location from a typical summer. There are few fires over Europe, but there are frequent fires in remote regions in Russia and in Canada. Here we see the view of the Norwegian Arctic Research Station at 78 degrees north. While the upper photo shows clear condition, the atmosphere is very hazy on the lower plot. This is due to the transport of biomass burning emission, which were led back to agricultural burning over Russia. They were transported within few days from the high latitude into the Arctic and led there to record high concentration in many combustion-related pollutants. In the year 2017 and 2019, something special happened in the Arctic. There were peat fires after ice melting and permafrost thawing burning in Greenland. They're rather small compared to fires in North America and Eurasia, but as they're very close in the Arctic, a lot of the emission can deposit it on snow and ice. In this case, the estimated total area was about 2.3 kilohectares, which corresponds to 23 tons of black carbon. 30% of it was deposited directly on the Greenland ice sheet. This is a very efficient climate forcer on a per unit emission basis. I showed now one case of direct transport of emission from Russia into the Arctic and an example of wildfires within the Arctic on peat areas over Greenland. As you certainly are aware of, in the year 2023 and 2025 there was a very intense wildfire season over Canada. With the help of satellite observation, we can estimate the emissions of black carbon, and by feeding these into an atmospheric transport model, we can calculate the distribution of the wildfire plume. We see how the biomass burning plume goes northward from Canada and then very frequently is located over Greenland until it reaches Europe in a couple of days. In the United States, there was very poor air quality reported by the media, which stemmed from the Canadian wildfire emission. Also in Europe, we could observe and measure the pollution which traveled previously over the Atlantic. Colorful sunsets are a sign that there are many aerosols in the atmosphere. However, during the two extreme years of wildfires in 2023 and 2025, we saw the plume is also moving frequently in the Arctic region. There the emission can have a climate impact when deposited on snow and also alter the cloud formation in the pristine Arctic atmosphere. There are ground observations in the Arctic which monitor the aerosols, but also satellites are a great tool to complement those observations. Here on the upper right we see a visual image taken close to the fire, which shows dense smoke. But with remote sensing we can also retrieve the atmospheric loads of pollutants. Here is an example where we see aerosols and carbon monoxide over the source region in Canada, but also stretching over Greenland. It's also important to know the vertical structure of the wildfire aerosol. Since a year, the EarthSky satellite provides us with information of the vertical structure of clouds and aerosol globally and also over the Arctic. Here I show an example of the wildfire plume represented in the atmospheric transport model, but also by the LiDAR instrument of the EarthSky satellite. The satellite tracks go from Russia to Greenland, and we see very nicely how the observed and model plumes are aligned. This is a valuable tool for assessing the impact of wildfires on Arctic climate. So these were many single cases where we see wildfire emissions in the Arctic area. The question is, how is the frequency of wildfires evolving and how special were those events? We have a very good information of how much has been emitted during fire events based on satellite products. For example, if we want to see how extraordinary the wildfire season in 2023 was, we can plot a time series of accumulated carbon emissions of all fires during the summer season and compare it to the emissions during 2023. There we see that already in the beginning of July, the released carbon was 3 times higher than during the last 2 decades on average. Here are some results from the last AMAP assessment report in 2021. The curves in the left panel show the emissions of black carbon from wildfires for different latitude bands. The blue line shows the development of high latitude emissions, and it is increasing. The question is, what causes these trends? Most of the factors are related to physical parameters, which stem from climate warming, but also human activity, which is extending to higher latitudes. Besides human activity, lightning also starts wildfire and is increasing in frequency. The fire risks get higher due to changes in precipitation, changes in soil moisture, but also thawing permafrost and the poleward shift of vegetation. To summarize, wildfires both have a climate impact but also can harm humans. There is a positive trend in wildfires which is connected to a warmer climate. Wildfires within the Arctic change the snow albedo. Wildfire emissions from high latitudes are frequently transported into the Arctic, and atmospheric observations combined with remote sensing are important to track the Arctic pollution of wildfires.
So we move on to the next presentation, and now it will be more on the observation side of it, while Sabine showed here many results from the modeling side of it. The next presentation will be from Mary Ruppel. She is a senior scientist at the Finnish Meteorological Institute and leading a project on Arctic wildfires and their particle emissions. So yeah, you can turn on the next video.
Honored audience, I will present now why black carbon deposition is important for Arctic climate and what Arctic black carbon sources are and what black carbon emissions could be cut down to mitigate Arctic climate warming. The climate effects of light-absorbing black carbon are amplified in the Arctic due to its deposition on high reflectivity surfaces. Black carbon decreases the albedo of snow and ice and thereby hastens their melt. According to some assessments, black carbon may have caused up to a quarter of the hitherto observed warming and melting in the Arctic. This photo has been taken from the Greenland ice sheet in summer 2014. Then black carbon particles originating from Canadian wildfires were deposited over wide areas of the ice. Black carbon is hydrophobic in nature and therefore it concentrates on top of melting snow and ice. Consequently, black carbon deposition hastens the retreat of glaciers all around the world. The majority of black carbon research in the Arctic has focused on measurements of atmospheric black carbon. Monitoring of atmospheric black carbon has been done systematically since 1989 and in one study even since 1968. Information on the trend of black carbon is essential to evaluate the role of black carbon in ongoing climate change. The monitoring shows that atmospheric black carbon concentrations have decreased substantially after the fall of the USSR and have stayed relatively stable since then in the Arctic. According to emission inventories, black carbon emissions from North America and Europe have decreased in recent decades, while emissions have increased in Asia. However, can we really conclude from these facts that the climate impact of black carbon would have decreased in the Arctic during the last decades? Our observations on black carbon deposition suggest that black carbon still plays an important role in Arctic climate change. Meteorological factors, mainly precipitation, greatly affect the deposition patterns of black carbon. 90% of black carbon is wet scavenged, meaning that it is washed out of the air by precipitation and is never captured by atmospheric measurements. Black carbon deposition has not been monitored in the same way as atmospheric concentrations have been, but the past deposition of black carbon can be determined from ice cores and lake sediments. So according to ice core and lake sediment records of black carbon deposition, its trend since the Industrial Revolution has varied significantly in different parts of the Arctic. Several ice cores from Greenland show that after a strong black carbon deposition peak in the early 20th century, black carbon deposition has decreased and stayed relatively low in recent decades. This has been due to improved combustion technologies and decreased emissions, mainly in North America. However, lower altitude Eurasian ice cores show similarities with the Greenland trend, but also increased black carbon deposition since somehow at 1970s or so. Such an increasing trend is also supported by European Arctic and northwestern Siberian lake sediment records. The differences in black carbon deposition trend within Arctic are explained by different sources of the deposited black carbon. Generally, more than half of the deposited black carbon originates from biomass combustion, including wildfires and domestic biomass burning. Greenland mainly receives black carbon deposition from North America, while the Eurasian Arctic from Eurasia. Furthermore, meteorological factors such as precipitation patterns greatly affect where the black carbon is deposited in the Arctic. This is an example from a Svalbard ice core. We compared the recorded black carbon variation in Svalbard ice with a known air mass transportation, which was available since 1948 to 2004. We observed that the increased black carbon deposition in the ice core was associated with increased atmospheric transport from Far East Asia, whereas in periods of low deposition, the source area of the black carbon was in Europe, but the particles were actually washed out of the air before reaching Svalbard. Now, an emerging threat in the Arctic is Arctic boreal fires. High latitude fire activity has increased with record-breaking fires occurring recently in both the boreal zone and in the Arctic. Arctic boreal fires release comparably large particle amounts due to them combusting soil organic matter by smoldering. The released particles are then deposited on the nearby snow and ice surfaces and, of course, hasten their melt. Furthermore, Arctic soil combustion may unlock long-stored carbon from permafrost soils previously considered as carbon sinks. Our newest results show that even thousands of years old carbon is released even by boreal and Arctic fires. To conclude, the deposition of black carbon is a key driver advancing Arctic warming and melting. The deposition trend increase in some parts of the Arctic and is not following directly the trends of emissions or atmospheric concentrations. Therefore, a conclusion of generally decreasing Arctic BC values or trends would be premature. Action to decrease adverse climate effects of black carbon in the Arctic should primarily target cutting down anthropogenic black carbon emissions in Arctic nations and in Asia. Arctic nation emissions should be cut down because within Arctic black carbon, emissions are more likely to deposit locally, and they have therefore a fivefold greater warming than equivalent emissions from lower latitude. And Asian emissions should be cut down since they are transported to the Arctic and they are increasing currently. The northward advancing and increasing Arctic boreal wildfires constitute an emerging threat because they release so many particles and they are deposited within the Arctic. Should new fire management strategies maybe be implemented with a focus on near Arctic fires? That is a good question. Thank you all.
Hello everyone, my name's Steve Arnold from the University of Leeds in the UK, and it's my pleasure to present at this AMAP session at COP30 on the topic of Arctic wildfire smoke and associated health impacts. High latitude wildfires are a frequent and naturally occurring phenomenon and are an important aspect of high latitude ecosystem function and play an important role in the carbon cycle. Variability in these fires is associated with variability in climate parameters, and so high latitude climate change has the potential to change the frequency and size of these fires. Some estimates suggest that heating being experienced in Siberia in particular is unprecedented during the past 7 millennia. This plot on the right compares the 2011 to 2020 mean of June-July temperatures with the 1961 to 1990 mean. And you can see this hotspot in heating around central Siberia, as well as general heating around the Arctic terrestrial regions. Estimates based on satellite-based fire emissions show that changes in fire area, as well as changes in fire emissions of carbon, have both shown a large degree of annual variability associated with climate variability over the last 20 years or so. However, there has been a recent increase in the frequency and in the intensity of these fires occurring in Siberia. These fires lead to important impacts directly in terms of danger to life and infrastructure, but they also lead to large emissions of smoke into the atmosphere. And this photograph from the press shows Yakutsk in Siberia being blanketed by wildfire smoke during summer. And this picture is somewhat reminiscent of pictures we might expect to see from regions where we think more are associated with air pollution exposure. This photograph is from New Delhi from this month in November 2025, showing pollution blanketing New Delhi. And this pollution is coming from different sources that we're more familiar with, such as industry, road transport, and solid fuel combustion in the home. So we're interested in wildfires in terms of human health because of their propensity to emit smoke, which comprises these very small, fine particulate matter that can be harmful to human health. So this picture from the US EPA compares the width of a human hair with the width of PM2.5 particles. And these particles are very small, and they're small to the extent that you may be able to fit around 20 of these PM2.5 particles across a single human hair's width. And exposure to these particles, we now have epidemiological evidence to link exposure to these particles to a number of respiratory and cardiovascular diseases. And that's because these particles are very small and they can get deep into the lungs and cross the barrier between the lungs and into the bloodstream. And a large fraction of deaths globally associated with several cardiovascular and respiratory diseases is now attributed to exposure to PM2.5 pollution. In our work, we were interested in understanding how wildfires at high latitudes affect human health. And here we concentrated on wildfires happening in Arctic Council nations, shown in dark blue. And for the United States, we concentrated on fires that are occurring in Alaska, and we neglected fires that are happening in the contiguous US further south. Our methodology combined satellite measurements of wildfire emissions or satellite-based wildfire emission estimates with an Earth system model, and we use a 20-year hindcast going back to 2001 up to 2020. And this allows us to estimate PM2.5 pollution coming from fires over this 20-year period, and we can then combine that with health impact assessment modeling and information on population to estimate health impacts due to cardiovascular and respiratory diseases. This study has been published recently, and you can access it using the QR code here. So our analysis shows that large fractions of particulate pollution on an annual mean at high latitudes are coming from high latitude fires. And you can see hotspots here in northeast Siberia and also in northern Canada, where around half or more of the particulate pollution annually is coming from these fires. For settlements, we can plot that as a kind of time series over the year, and we get information on how much pollution from fires is increasing the total amount of pollution in the atmosphere in these settlements. So here you can see two lines. One is the solid line, which is the total pollution being simulated in Yellowknife as an example. And in the dotted line, this shows the pollution that would be present if the fires were not there. And we have this information for hundreds of settlements now across the Arctic, in Canada, Alaska, Russia, and Northern Europe. This also showed an interesting trend over the 20-year period, especially in the central Siberian region, where there's been a substantial increase over time, over that 20-year period, in the PM2.5 pollution that is coming from wildfires. So our health impact assessment modelling shows that around 13,000 Arctic residents per year are dying prematurely because of their exposure to wildfire smoke. Interestingly, our analysis also shows that around 8,000 people in non-Arctic nations are dying prematurely due to exposure to wildfire smoke, which is coming from Arctic nation fires. And this is because of long-range transport of that smoke from the Arctic Council nations further south into nations where there are more populated regions that are succumbing to exposure to the smoke. If you look over time, you can see the health impacts that we assess and we estimate for Arctic Council nations in blue, and in other countries outside of the Arctic Council in red. What's interesting is that our analysis seems to suggest that the remote impact, i.e. the impact on residents in non-Arctic nations, has actually been declining over time. The reason for this, we suggest, is that the fires, although they've been increasing and the emissions from the fires has been increasing, they've actually been moving further north. And that smoke is now being emitted into latitudes where there is less impact on human populations. And that also means that the smoke is less likely to be transported further south to impact on residents in more populated regions further south. So our analysis suggests that wildfires in Arctic Council nations have substantial local and remote health impacts. Our analysis also suggests that fire emissions are a major factor in determining Arctic population exposure to air pollution on an annual mean basis, and they often dominate the annual mean PM2.5 pollution exposure in many settlements across the Arctic. We also recognise that there are large uncertainties, especially when we think about health impacts on Arctic populations, and that's partly because of poor knowledge of smoke toxicity, and also poor knowledge of underlying health of Arctic populations, i.e. how susceptible these populations are to the harmful impacts of the smoke. So thank you for listening. I'm very happy to receive comments and questions at my email here. So thanks.
So let me first ask the first question to you, Chief Bill. Tell me about where you come from and how the wildfires have impacted your region.
Yes, thank you. My name is Chief Bill Erasmus. I'm from Northern Canada, from Yellowknife. We are Athabascan people. I am Dene, and I'm a member of the Yellowknife's Dene. So we have two communities that are adjacent to Yellowknife, the largest population. As you could see on the screen with the videos, we've had a lot of fires in the last few years, and the most recent devastating fires were in 2023, where almost 80% of our population in the Northwest Territories had to leave. They had to evacuate. And they went to other northern communities, but the majority had to go south. And there's only one highway going south, or they had to fly out. and they went as far as 2,500 kilometers away, as far as Manitoba. So people were impacted. It was very it was a very complicated experience because many of these communities had never evacuated before, and in terms of emergency management, it wasn't clear who was in charge, and so that's what compounded the whole problem. For example, we have chiefs that are the leaders, and we have our own governments, and then there's the municipal governments where there are mayors. Part of the problem we have, it's a political one, where the legislation only recognizes the municipalities or the mayors. So you may have a community that has a majority of our people, but the chief is not in charge. So it caused confusion, because if something happens in our communities, we don't go to the mayor, we go to the chief. And so what we're trying to do now is to set up protocols so that those two legal entities are able to determine how they're going to react when an emergency is declared. Because it's going to take time for the legislation to change. It was really impactful. For example, there was one community in 2022, they had to evacuate because of flooding. Okay, so 2 weeks away from our home, they come back. Less than a year later, there's a fire where they have to evacuate. They're away from home 2 or 3 weeks, they come back. There was another fire, the wildfire that came from a different direction. So they had to evacuate 3 times in less than 16 months. So you just imagine, how do you react to that? We've been experiencing droughts, less rain, less snow, and that's having an impact. We have one of the longest rivers in the world that goes all the way up to the Arctic Ocean. It's called the Mackenzie River, and normally people bring in their supplies by boats, by barges, and for 2 years they were unable to bring supplies up because the water levels were so low. And that's partly because of the rainfall, but it's also because there are dams south of us that prevent the water from coming down. Plus there's the tar sands development of oil and gas, or oil. To develop 1 barrel of oil, you need approximately 3 to 4 barrels of water. So they consume a lot of water upstream from us that affects us in the north. Those are just some of the impacts.
Yeah. So your people have a long history of using indigenous knowledge, traditional knowledge, to deal with changes that happens. But how is this different from before, and can you use that knowledge in the future to adapt to these changes?
Yeah, we have our own traditional burning practices that was outlawed, and we were unable to continue to do that for many years, and now we're being encouraged to reintroduce that. And my father, for example, I witnessed how he would burn the grass and the top, like we call them deadfalls, where trees fall. He'd do that in March, at the end of March, when there was still snow, and he'd be very careful with the wind and everything, but he would burn the area, and what it would do is it would get rid of all the old growth, And so very seldom would fires start because of lightning or otherwise. And so that's what our people normally did. And because they didn't do that, now the forests are really thick and fires start and they're really hard to control.
Question to you, Rolf, and how AMAP is using indigenous peoples and in knowledge of dealing with climate impacts like such as wildfires. Can you talk a little bit about that?
Thank you, Maria. And I guess I could start by saying, like, it's well, do you hear me first? I guess I can start by saying, like, indigenous peoples have been integrated into the work of Arctic Council and AMAP since the very beginning, in the terms of being permanent participants. So it's more than just observers. They are there for a permanent reason. And they are in AMAP. They are working together with the experts and the heads of delegates on the same level to provide a good basis of knowledge, regardless of whether it's like what we call science or whether it's indigenous knowledge or local knowledge, to bring forward the best information available on these issues. So we try to, when we make our assessments, which I told a bit about earlier, we try to bring in both the scientists and the indigenous knowledge holders and see what we can bring forward. Because indigenous knowledge often have a much better resolution. They have, it's on a very fine scale, both when it comes to space, but also when it comes to time. Like Chief Bill said, like, they have a long tradition of this knowledge. And they know exactly in the landscape where fire will happen, how that will take place. And it's very good when we try to predict, for instance, the change in wildfires by predicting the change in the landscape and to see how that can actually affect whether wildfires will be increasing in the future or whether they will be decreasing or stable. So we try to bring this in every stage, but also when it comes to communicating this to policymakers, because it is something, it makes something different hearing Chief Bill's stories about people that has to move away, people that are affected by this on their lives, than more than just the number. So when you combine those things, it's a very strong message to policymakers.
Thank you. We have room for one more question, and I was thinking of asking you, Chief Bill. We are here in Belém, COP30. It's called the Nature Cup, it's called the Action Cup, which I believe both are relevant for where you come from. How do you see that these global international efforts can contribute to what you are experiencing where you come from? Why is it important to be here?
Yeah, I hear many people talk about not knowing what to do as individuals or as communities, and they're depending on their government to do something to make change. And I think we as individuals have to do our part. We need to recycle. We need to use compost. We need to get away from fossil fuels and so on. We need to make that commitment as individuals and as families and as communities, because we can't wait for the greater nation to make those decisions, because it's we're in trouble if we do that. So I think we need to make that commitment. Like, it's so obvious up north. Fires used to start in maybe late June and end at the end of August. But now they're starting in April. There was a fire that just started in October, last month, at home. So fires are going till the end of October now. So it's so very obvious. We have winter roads. Some places don't have all-weather roads. It doesn't get as cold as fast as it used to. So the winter roads, we're losing a month at the beginning and we're losing a month at the end. So it's real. And those that deny it really have to go up north to experience it.
That's a great message. And with this, I just would like to thank you for being here and for telling your story, and for Rolf to be here. And thank you all for listening.